Hello, everybody.
Shared again?
Hello, everybody. Welcome to the November meeting of the Howard Astronomical League. It's
Don't
it's-
forget to share.
Thank you.
Sharing.
It's great to see so many people actively engaged in helping me set up. Can you see the screen now?
Yes.
Okay, great. Thank you. Let's do that record scratch thing and start again. Welcome to the November Howard Astronomical League meeting. It's great to see so many people and some new faces here at the Robinson Nature Center, and it looks like we have a pretty good contingent online, so it makes me very happy. Tonight we have a pretty interesting meeting, I think. Here's our agenda for the evening. I'll make a couple of announcements, including, well, I'll talk about it in a second, but I'll talk about our December meeting, which is going to be kind of fun. It'll be here, potluck. And then we have three club members, Vice President Jim Tomney, President Victor Sanchez, that's me, and former President Jim Johnson. We're going to go through some topics. It's not a comprehensive by any means review of amateur astronomy, but we'll go through some topics maybe helpful to new people and maybe helpful here and there to people who have been doing this for a while. And then we'll do our regular thing, which is what's out in the sky this month, but we have a special topic this month. One of our sister organizations members, Chris Bennett, has put together some. Are you in the room, Chris? Okay. Is it okay if I actually show your slides?
Yeah.
Okay. So he's going to talk about NGC 206, which is a pretty cool star cloud, and well, I'll let him tell you about it. And then we'll do our normal shallow sky and what's up in space, and then go through some pictures, including a very small tutorial from Ian Slepian on the process of putting a mosaic together with the sea star. So without further ado, this is tentative, but just to get you started, David Stein, our public outreach event coordinator, put together the schedule. Usually he does that, then the club members or the board goes through it, and we review all the dates and make sure there's nobody has a issue with anything. But I think he always does a really good job of putting this together. So nominally, here's our public and private and members only star parties scheduled for 2025. We'll get it, officially up on the website and all that soon. The only recent event was the weather's been a little off, so there haven't been very many impromptus this last week or two, but we had a public event at Alpha Ridge, our last public star party of the year. Bill Whitebloom was there. Dale Gent was there in the observatory, showing people sites with the ILIG scope, and we had like 15 telescopes and over 250 people, so it was a pretty busy and fun event. I was not there because I had to be somewhere else. Okay, so which makes me sad because I love going to the star parties. It's a lot of fun for me anyways. So December meeting, it's you don't usually talk about the next meeting when you're starting this meeting, but this is a fun one because it's our end of year. We'll have tables set up here. We'll have some potluck. People will bring in whatever they want. You can see up there some of the items people have brought in the past. And it's not going to be a formal meeting. It's just going to be just talk and kibitz and talk about what you're doing and whatever gear you're working on. There are also sometimes people bring in gear to swap meet or to sell. And this year we had a former member who donated some items, including some pretty nice eyepieces. So we're just going to raffle them all off. The Teleview Fossil and Panoptic and D-Lights you can see up there. So we got 4 eyepieces. I'm going to give everybody a raffle ticket or a couple of raffle tickets, and you can put them in the bin for the one that you want, and then we'll draw names at near some point in the meeting. So if you are interested, I'll send out an email to the club. If you're interested in coming, then I'll ask you to send me an email so that I can have a head count and know how much how much food is coming and do that kind of organization. So stand by for a message about that. Okay, so I left out something in my I just realized I left out something in my agenda, which is the first thing we usually do, which is new member or new people introductions. If anybody's interested, I see a lot of new faces. So if anybody would like to just introduce themselves uh, online or in the room.
Hi, good evening. My name is Sanchez. I'm not a doc. I belong to the Westminster Astronomy Society. Been there for many, many years. I used to be the director of the planetarium there, member of the board. I love astronomy. My passion is archaeastronomy, is what I tell you.
Okay,
Is that I used to the planetarium. And I have little C-star 50 that I've been using, give up the optics. So
that's
sitting in the inside and watching stuff on your phone is much better than sitting out in the cold.
fantastic. Thank you. I see we got the WAS contingent over here.
Jeff Silver, know a few people at this club. Ian is one of them. Can't think anybody else offhand. I'm also part of the Westminster one, so got two clubs now, and just wanted to meet some more people and have another place to go, and just looking forward to it.
I love it.
Was out at Alpha Ridge several times before I joined either club, probably about 8 years ago, 10 years ago.
That's I like the idea. I'm so happy that Ian reached out and I love the idea of more collaboration with the clubs.
Great.
So welcome, thanks. And
I'm
Chris.
Chris, also from Wassing. I've been up to.
Speak of the devil.
I've been up at Wassing for years since I moved up to Sykesville. I did live in Ellicott City years ago, so I have been there a few times years ago. So,
Okay, well, great. Well, I think just more diversity, more other sites to look at, more events. So that's great. I'm glad you're here. And Ian, thanks for coming too, and thanks for coordinating the WASI connection. Anybody else new in the? Yes.
Hi, my name is Jason Goldstein. I was a member of this club like maybe 8 years ago or so. We left the area. Now we're back. I have a C-Star and in my car an ADC that I need collimation help with. So I figured can't do that online.
Terrific. Welcome. Yeah, I think if you come to some of the members events, that's generally when people have time to kibitz once they get their stuff set up, and maybe somebody can give you some hints or, socialize at the meeting or after the meeting and get some tips and tricks on collimating. Yes, ma'am.
My name's Aileen Judd, and I decided I wanted to try to become a better photographer in retirement. And so I thought that if you can learn how to use your camera at night, you might get better at it. And so that's what I'm trying to do here. So I found this club and I'm going to see where it takes me.
So welcome. We have a member named Cheryl Kerr who has walked those footsteps. So at some point, maybe you can reach out or we'll get you guys in touch, because when she first started, that was exactly what she said. And her astrophotography is started mostly with like Milky Way, wide field stuff, simple, camera on a tripod, none of this fancy tracking, all that stuff. So I think you might find it useful to speak with her. Yes, sir.
Yeah, I'm Jim Kaiser. I'm a returning member, and I guess I've been a lifelong amateur astronomer. 69, started when I was 9, and my brother gave me a mirror when I was about a friend of his or a colleague of his had made a mirror, and he gave it to me for my 14th birthday, and that turned into a telescope. And then I've just recently built one. With the help of Guy Brandenburg. I don't know how many of you know him. He's the president of the National Capital Astronomers. So he has a telescope making operation down in Chevy Chase Community Center. which is a guess. He is amazing. If you want to be in touch with Guy, you just talk to me.
That's
Guy
fantastic.
is- Yeah,
That has been missing from there was a number of
telescope making.
telescope making, there was a contingent a while ago that was interested in that.
Yeah,
And it has left the club, so that welcome back, and maybe you'll pique some interest amongst other newbies.
well, I mean, down Chuck E. Cheese, he runs it twice a week. He's always there. So I can tell you about that. It's great. He and his colleague Alan, they will take you from nothing to a telescope.
Huh.
They know so much about making Dobsonians, and the guy has supervised me, polishing and figuring a mirror that I'd already started. I'm in the process of making another one just because I like it so much.
Awesome.
Yeah.
Folks online, can you hear us okay in the room?
Yep.
Okay, thank you. Yes.
Dave Lomakowski, I've been professor at CCB, Cates for over 20 years. I direct the planetarium over there and wanting to see what you guys are about. I've had a couple of star parties here and there, just haven't had the time to do it. My wife thought it was nice enough to humor me to come along, so.
Wow, welcome, thanks. What a crew we've got tonight. This is great. You want to come up and teach some of the stuff that in our
I
anybody
can help out.
anybody else? Okay, well, great. Anybody online want to say hello?
Hi, good evening, everybody. My name is Jason Oswald. Kind of fell in love with space after I saw the Interstellar movie. I'm really new at this, and I'm glad to join this club and looking forward to meeting everybody.
Fantastic. Okay, so I just did something. Let me undo what I just did.
Wow, this is really an incredible first time group. Everybody, love you.
Yeah, I actually just joined 2 days ago, so I'm super new at everything.
Okay, well, hopefully this will be helpful. All right, so without further ado, I think we're going to move on to the featured speakers. So Jim, do you want to share your screen or?
Yep.
Okay, oh, I need to set that down.
Yeah, you gotta turn it on.
Okay, you're good. You should be good.
So let's see here. Shrink this thing up. All right, everybody seeing it okay?
See the first cover slide.
The cover slide, Naked Eye Astronomy.
Yes, I see it.
Okay, and folks in the audience there, you're good?
Yes, we're good here now.
All right, good. So basically, learning the sky is important. I don't care about whether your scope is go-to or not, all this wonderful technology where, you don't have to do a thing. But I would argue that you really do want to be able to find the Big Dipper. You want to know if Orion is out tonight. And, what's that bright star in the west after sunset? You don't want to have to drag out the telescope and have the computer tell you. You want to know yourself. So, and honestly, once and only once you kind of have this feel for the sky, should you really think about buying a telescope and kind of going further. To me, buying a go-to telescope without knowing the sky first is a bit putting the cart before the horse. So that's kind of like what this little presentation here this evening is, to kind of get you oriented a little bit, hopefully. So we're going to talk about what we see we'll start off by talking about what we see during a night. And I'm going to use the application known as Stellarium. It's a planetarium software. And it's free as a download, or you can use their web app, which is also free. And so here you're looking at what the sky might look like about an hour before sunset. And so really your first step is you want to be able to identify your cardinal directions. You want to know where's west, where's north, east, and south from where you're observing. And you can certainly use the sun as roughly where west is. Keep in mind, this time of year, you can see here's west over here, here's the sun. So during the winter, the sun is going to be left of where due west is. But, you know, just get a decent approximation of where these cardinal directions are. So as the sun starts to set, you enter into what we call twilight, and you've got three recognized stages of twilight. You've got civil twilight, which is probably kind of simulated here, nautical and astronomical. They all depend upon how far the sun has sunk below the horizon, with astronomical being 18 degrees. And at that point, you have removed all of the light from the sun into the night sky. So in other words, it's not going to get any darker by the time you reach astronomical twilight. The first thing that you would see, and again, this is contemporary, this is for this evening or tomorrow evening or next week, you're going to see Venus. That's going to be a very bright star that you're going to see left and above of where the sun has set. So, and as it gets dark, let's turn 90 degrees and look north. And you probably, when you say look north, you're probably thinking, oh, great, where's the North Star? You know, the North Star, is that it over here, this really bright thing down here? And the answer is no, it's not. And that's a common mistake for a lot of people. They tend to think of the North Star as the brightest star in the sky, but it's not. Its claim to fame is actually that it is steady. It never moves. All the other stars are going to move during the night and during the year, but the North Star, also known as Polaris, that's going to hold constant. That is not going to shift its position once you identify where it is. All right, so where is Polaris? You know, one of the things is trying to figure out, when you see all of these stars, you've heard of the Big Dipper, but where the heck is the Big Dipper among all these stars that you're seeing? Well, if we add in the constellation lines, it becomes a bit easier. And we can see that, okay, right now, this time of year, the Big Dipper is pretty darn hard to see. It's actually down low along the northern horizon. And in this particular view here, the edge of the bowl, which is what will point us to Polaris, that's actually partially hidden by our fake tree here. But this is, from my personal backyard, I would probably not see any of this. So it kind of depends on your location. But the takeaway here is, this time of year, it's going to be a little hard to see the Big Dipper. If you can visualize it, you can use those bowl stars, the pointer stars, to more or less point you right in the direction. And here is Polaris, or the North Star. And it's really a fairly ordinary looking star. Nothing exceptional about it, except for the fact that it doesn't move through the night. So let's throw on a couple names here of what we're seeing in the evening sky in the north. We've got Polaris, and then down here we have the Big Dipper. We've got over here a very bright star called Capella. And when we want to talk about brightness, that's an important concept for you to kind of wrap your mind around. So there are, it started off back in ancient Greece. Hipparchus said, I want to take all of the bright stars and I'm going to call them first magnitude. Then anything that's kind of dimmer by half, I'm going to say is second magnitude. And anything dimmer than that by half, I'm going to call third magnitude. And this went down to sixth magnitude, which is the limit of naked eye visibility. The ancient Greeks, that was a wonderful swag. But in reality, as science became more and more precise, astronomers said, no, that's really not going to work. So they decided that the star Vega, which we can see in our skies, is going to be magnitude 0. And then from there, anything that is 2.5 times dimmer would be first magnitude. 2.5 times dimmer than that would be second magnitude, and so on down to the sixth magnitude. And just to make things even more complicated, Vega is not the brightest star in the sky. That honor goes to Sirius, the dog star, and that is at magnitude -1.4, I think. So here's the takeaway if you're a new astronomer. There is something called the magnitude scale that helps you expect how bright something's going to be. And the larger that number is, the fainter that object is going to be. So Capella over here was 0 magnitude. It's actually 0.08, so very close to Vega. It's like the 3rd brightest in the northern hemisphere. There are no first magnitude stars as we're facing north, but we do have several second magnitude stars. The stars along the Dipper in its handle and Polaris itself. Those are second magnitude stars. You can then also see part of the bowl of the Little Dipper, and this is a 3rd magnitude star. And this, of course, is going to depend on your light pollution. If you're in Baltimore City, you're going to really struggle to see this star here. You might even struggle to see the bowl, the handle of the Dipper. You certainly could be able to pick out Capella. But a lot of this is light pollution sensitive. So the further out you are, the better you're going to be able to see these stars, which is why we go out to Alpha Ridge a lot of times, because it's a little bit better out there. From your own backyard, a couple of tips that we can give you as a new astronomer. First of all is, try to avoid bright lights. Try to find a section of your yard or a nearby park or someplace where you're shielded from some of the brighter street lights and stuff. The second thing is make sure that you give yourself time to adapt. As you are sitting out in the darkness, your eyes are actually, there's a biochemical process going on that enables you to see fainter and fainter things. So give yourself about 20 minutes to get what we call dark adapted. And then finally, if you don't look directly at an object, if you look a little bit off to the side, you'll find that your vision there is more acute. It's a little bit better for seeing faint objects. So that's another thing called averted vision that sometimes will allow you to see a fainter object. And then we get down to the 4th magnitude stars. I know from my backyard in Towson, it's extremely hard to catch one of these naked eye. And this one here is rather than a long tongue twisting name, this is Epsilon Ursa Minoris. So that's still a long tongue twister, but what does that mean? That name, there's actually kind of like some information in that name. So the first thing is Epsilon, that's a Greek letter. And the constellations, the brighter stars, are all have Greek letters assigned to them, starting with alpha, the first letter, beta, gamma, delta, epsilon. So, and that also is by rank of brightness. So if I say Epsilon Ursa Minoris, that implies this is the 5th brightest. That's the 5th alphabet item of the Greek alphabet. This is the 5th brightest star. And Ursa Minoris, that is actually the name of the constellation, the Little Bear. And constellation names are all in Latin. And so if I were to say Alpha Auriga, that would mean Capella, the brightest star in the constellation Auriga. So these sort of names where you have the Greek in it give you a hint as to the brightness in terms of within the constellation, but it is not foolproof. There are more than one instance where they've got it mislabeled, and you'll, for example, find that the beta star is brighter than the alpha star. But as a rule of thumb, that's a little piece of information that you can get just from the name. So, we're talking about the Little Dipper. Here's the Little Dipper. We can see it looks like a dipper, and the Big Dipper. But that's different. That's an asterism as opposed to a constellation. So an asterism is something, it's a grouping of stars, and they don't have to be all within one constellation. That kind of is something that you would look at and go, yeah, I can recognize that. I get that that's a dipper. I get that that's a triangle. I get that that's a hexagon. As opposed to a constellation, which, to be quite honest, the ancients had amazing imaginations, or we're smoking some very powerful stuff. You know, to take these few stars here and make a giraffe out of them is a great leap of imagination. And I don't know about you, but I've never seen a bear with a tail like that. So, you know, there's a difference between asterisms, which are something that you'll kind of go, oh yeah, I can make that out, versus a constellation, which is the more formal boundaries and identification of these grouping of stars. All right, let me catch up with my notes here. So let's,
Question,
yes.
why does Polaris not move?
Basically because the Earth's axis, which we rotate around, it's basically pointing to that point in the sky. So, you know, as if you were standing at the North Pole and you looked directly up, Polaris would be pretty much directly overhead. Okay, we are at latitude 40 degrees. So that means Polaris is 40 degrees up from our horizon. And so everything will basically pivot around Polaris as the Earth turns. Does that make sense?
Yep.
All righty. So let's take a look at how the night sky advances at different times. So here we are starting out, you know, astronomical twilight. We've got the Big Dipper down here, Capella over here, and the W, here's another asterism of Cassiopeia, the queen. Let's go out around 10 o'clock and notice that the Big Dipper has now swung upwards. Cassiopeia is high overhead, and Auriga with Capella, that very bright star, is off our screen here. It's almost directly overhead. And now we've seen that this constellation has swung down. So the bottom line is everything is rotated. Let's set the alarm and get up for 5 o'clock in the morning. And now we can see the Big Dipper is almost overhead. It's arching to go directly overhead almost. Here comes Capella and Perseus. These guys have now swung down into the western sky. So you can see that as the night progresses, everything is rotating around Polaris. So here's a little video to help reinforce that. Here's the Big Dipper. I don't know if you can make it out. This was obviously a nice dark sky site where they made this video. And if we follow the Dipper, this guy here should be Polaris. So let's put the video in motion. And sure enough, this star here is not moving, but notice the Big Dipper swinging lower and lower. So clearly this was taken like in summertime, as the Big Dipper was gradually now heading towards its low swinging through the northern horizon. So that's just an example of seeing over, you know, condensing a few hours of time into a video that help reinforce this idea of these constellations swinging around Polaris. All right, I'm done. Come on. There we go. So now the other thing that we want to talk about, we've talked about a diurnal motion, or in other words, a motion of the Earth due to its rotation. What about the Earth's orbit around the sun? Well, that's going to impact what we're seeing in the sky as well. So here we see what the sky looks like at midnight on the first day of winter, this winter solstice. And you can see that there are some very prominent constellations here. And we as astronomers tend to kind of like group constellations with the seasons. So if I were to group constellations of winter, they would include Orion, Gemini, Taurus, Canis Major with bright Sirius here, Auriga, and even Canis Minor. So all of these guys here are kind of like your winter constellations that you want to get familiar with. If we do midnight on the first day of spring, we've got a new set of constellations. All of our winter guys are kind of over here on the western horizon, but we get Leo the Lion, and we get that Big Dipper overhead. And we also have coming up in the east, Bootes and Virgo. And often one of the tips that you will hear is you follow the handle of the dipper and you arc to this star called Arcturus, and you speed on to Spica, which is in Virgo. But the bottom line is you have a collection here of spring constellations. Same thing for the summer. If we go out at midnight on the first day of summer, we've got Sagittarius and Scorpius, the heart of our Milky Way, low on the southern horizon. We've got Lyra and Cygnus and Aquila rising in the east, and they make up the summer triangle with Deneb, Vega, and Altair. That's a very prominent asterism for the summer. And again, as I mentioned, asterisms don't necessarily obey constellation boundaries. Here we're at making it up with 3 constellations. And then finally, we come back to fall, and we've got basically, it's the story, if you've ever seen Clash of the Titans, that movie, the story of Andromeda and vain Queen Cassiopeia and Perseus flying to the rescue and slaying the dragon, the sea monster. All of these guys are in the constellations here. We have Pegasus, we have Andromeda, we have Cassiopeia, we have Perseus. Other constellations of the spring are also Aquarius, Pisces, which is quite faint, and Capricornus. So you get to see, and again, here come the winter constellations back. There go the summer constellations over here. So tonight, if you start off on the left-hand side, we still have summer constellations in the sky. We've got our fall constellations rising. Go out before dawn. Here are your winter constellations setting. Here are your summer constellations rising. So basically, over the course of one night, you get to see probably a little better than 3/4 of the night sky. You start off with your summer season and you end up seeing some of the spring season. There is, of course, a wedge where the sun is that you're not going to be able to see. So another important kind of concept here, as you gradually start identifying your constellations, you're going to want to pay attention also to the 12 special constellations that make up what we call the zodiac. And the zodiac is basically the constellations that a planet or the moon or the sun can appear in. So here, again, this is our sky, roughly this evening at midnight. We would see Saturn in the constellation of Aquarius. The next zodiac constellation is Pisces, then Aries. Taurus has got a little bit of a traffic jam this evening with Jupiter and the moon. And then a little further over, we go through Gemini, and Cancer has Mars this evening. So the other, if we were out even earlier in the evening, we would have seen Venus in the constellation Sagittarius. And the other zodiac constellations are, let's see, Virgo, Libra, Leo, Capricornus, and Scorpius. They're not visible on anything here. But you will want to become acquainted with these constellations. Some of them, like Taurus, are quite easy to see. Others, you may want to wait for a planet to get inside of one of them to help you identify, okay, this is Pisces or this is Aries, because I know that Jupiter or Mars or Venus is in it. All right, here's another imaginary line that you want to become familiar with, and that's the meridian. Basically, the meridian is what's going to divide your sky into a western half and an eastern half. And so once you, again, we're kind of building on things here. Once you've identified Polaris, if you drop a line straight down to the northern horizon and then go back straight up, that line basically would bisect your sky into a western half and into an eastern half. And any object that crosses the meridian, such as this star here, that means that it's at its highest point in the sky. So that's your best opportunity to take a look at that particular object. So again, kind of talking about celestial motions here, let's look at Rigel, which is a bright star in Orion, and it will reach the central meridian on November the 17th at 1:35 in the morning. Okay, it will cross that point. It will be at its highest point in our sky. If you go out the next night and you go look at 1:35, well, it's not on the meridian. It's a little bit west of it. You go out the next night, it's even further west of it. And so basically, you know, with 24 hours, you have 1,440 minutes in a day. If you divide that by 4, you get 360. Okay, so that is the number of degrees in a circle. So it makes sense then that basically every night you're going to have that star come to the meridian 4 minutes earlier. And in fact, it doesn't matter where in the sky, I'm just using the meridian because it's convenient. But if you were to set up your telescope at like 1:35 in the morning and you've got Rigel in it, you would need to go back out the next night, no matter where it was, at 4 minutes earlier, at 1:31. And so the takeaway for you is in 1 week, an object is going to be roughly a half hour earlier. So in other words, you'll have to go out 30 minutes earlier a week later to see that star or that object in the same place. If you go a month, you're going to have to get out there 2 hours earlier in order to see that object in the same place of the sky. Here's another concept, which is called opposition. So basically, that means that when the sun is setting, the object is rising in the east. So here on December the 7th, we will have the situation where the sun is setting, but Jupiter is just rising. So we would say that Jupiter is at opposition. In general, that is the best time to take a look at an object. It'll be in your sky all night long. It will set when the sun is coming up the next morning. And Jupiter and Saturn will have opposition once a year. Mars, because of its motion, not once a year, but the objects that lie inside of Earth's orbit, they cannot get to this geometry where the sun is setting and they are rising. So things like Mercury and Venus, they will have what we call greatest elongation. In other words, the point at which they get the farthest away from the sun that they can appear in our sky. And for those inner planets, greatest elongation is the point where they are best positioned to see. So another important tool in your toolbox when you're exploring the sky is being able to measure the sky. And if you'll pardon the pun, you have a tool at hand that is very convenient. And that is basically you take your hand, stretch it out in front of your body. If you raise your pinky, that represents roughly 1 degree of sky. If you put together your middle, index, and ring fingers, that will approximate 5 degrees. A fist is going to be 10 degrees. That motion there, which I can't really produce with the arthritis in my hands, is 15 degrees. And if you do hang loose, you've got 25 degrees of sky. And again, these are approximations, but when Sky and Telescope or somebody saying, oh yeah, you know, it's 10 degrees south of Aldebaran, it helps to be able to go, okay, well, I've got a rough swag of how much distance that is. All right, so I'm going to put out a learning plan for you to build upon all the little stuff that we've kind of talked about here. So step 1, as we started at the beginning, go out, you know, kind of find where you want to observe, check out sunset, or, you know, grab a compass. You know, you can even download an app on your phone for where your north, west, south, and east are, but get oriented, you know which your general cardinal directions are. Then for this evening, again, this is kind of contemporary for the next few weeks, locate that W asterism, locate Cassiopeia. That W, all of its stars are second magnitude. So you know, you should be able to see it from most locations. You might not be able to see it from downtown Baltimore, but everywhere else, you should be able to catch that Cassiopeia looking up, okay? The Big Dipper's down, Cassiopeia is up in the sky, not directly overhead, but up at like maybe 50 degrees high. Then you can give it a try to use Cassiopeia to find Polaris. So the slightly longer part of the W, if you bisect that, you can get it over to Polaris. And how would you confirm that it's Polaris? You know, if you go out and you go, okay, I think that one there is Polaris, the thing to do is go out 2 hours later. Is it in the same spot? It's Polaris. Has it moved? Not Polaris. And then the other thing that you want to start off doing is once you've nailed Polaris, kind of in your mind's eye, figure out where that central meridian is. You know, one of those, again, imaginary lines that'll be helpful to you. All right. Hey, and as a tip here, we live in an amazing time where, you know, there's an app for everything. If you were to search constellation on your smartphone or on your tablet, odds are that you're going to find many applications. And these things can be really helpful because you can kind of aim them at the sky and they will tell you more or less, hey, that star there, that's Saturn. Or, hey, here's, you know, the great square of Pegasus. So this is really a helpful tool as well, beyond just like the paper star charts that you may find in Sky and Telescope or Astronomy. All right, so step 2, let's go find some planets. This is relatively easy. If you just simply look after sundown, once it starts to get a little bit dark in the southwest, there is a can't miss -4 magnitude star, and that is Venus. And, you know, it's kind of fun then over the next several months to kind of look for Venus, because what you'll find is that, you know, long about springtime, it's going to disappear from the sky and it's going to reappear in the dawn sky. So track down Venus and kind of keep an eye over the next several months. Now let's try to find Saturn, which is a little bit more challenging because it's only first magnitude, but it lies on the meridian. So again, building upon you found the meridian, if you look at the meridian and you look roughly halfway up at 7 o'clock this time of night, it's going to be on the southern horizon. Look, southern horizon, halfway up, there's going to be a first magnitude star, and there's not going to be much of anything else around it that's that bright. And another way is that the moon joins Saturn on the night of December the 7th. So if you're not having luck or you're not sure, wait for the moon to join it on the night of December the 7th. Here's a thing to keep in mind. If you don't do this like tomorrow night and you go out a week later, remember, it's going to be a half hour sooner. So 2 weeks later, you're going to have to look for this on the meridian at 6 p.m. So just kind of keep that in the back of your mind that as time marches on, the planet will appear on that meridian sooner and sooner until it's happening during when the sun is up. For look out for Jupiter, very easy again. Go outside around 10 o'clock, look to the east, and you're going to see a very bright star. And if you have a pair of binoculars, it's worth getting them out and taking a look at Jupiter, because you will likely see some very small stars very close to it. And those are the brighter Galilean moons, which you can actually see with your binoculars. You don't have to have a telescope to pick up on them. All right, so now that we've got those kind of somewhat easy things under our belt, let's look for some winter constellations. So let's start off. We've got Jupiter, and we know that Jupiter is within Taurus. So we know we can kind of see Taurus by doing that. And if we look to the left of Jupiter and roughly at about the same height, the same altitude, we're going to see an orange star, and that's Aldebaran. It's a very pretty star. And if, again, you have your binoculars, it'll be very evident that it's an orangish color in them. So again, jumping off from Jupiter, look above and to the left, you should see that bright star Capella, and that's part of the constellation Auriga. And then if you go south, which would be to the right, and a little east of Jupiter is Orion. And Orion is a very iconic constellation, and you can recognize it by 3 stars in a row, and that's his belt. So hopefully, with going out around 10 o'clock at night, you'll be able to start off by identifying those 3 major winter constellations and major stars. So finally, as your final challenge, let's try identifying a couple deep sky objects. The Pleiades, which is also known as M45 or the Seven Sisters, this is without doubt the best known star cluster. And right now, with Jupiter as your guide, it's a good time to find it because, again, using your hands, you will find it about 20 degrees to the right and above of Jupiter. It's going to look like a little dipper if you are in slightly dark skies and have some good eyesight. Again, go back and use your technique of being dark adapted and even using averted vision if necessary to track this down. Okay, if you have found Orion and there's 3 belt stars, look about 3 degrees south or basically right of the belt for a glow. And this is, again, early in the evening. If you look later in the evening, it won't be right, it will be below the belt. So this is the Orion Nebula. And again, this might be kind of hard to see. This is the faintest object that we're challenging you with here. And the best thing is if you have a pair of binoculars, you want to take a look at both of these objects because they will really look impressive, especially starting out in a pair of binoculars. So it's up to you. Use these skills to begin to identify all of the major constellations. Make it a point, make it a New Year's resolution. You're going to go identify 15 constellations this year and 10 bright stars. As you do that, you will then find that when you look at a star map, you'll feel more confident in being able to identify the fainter stars and the fainter constellations, which will lead you into finding fainter deep sky objects. The other tip is you can also use the moon as it goes through the zodiac constellations to help identify some of these constellations and objects. And the best joy of all of this to me is that you become aware of that relationship between our seasons and the constellations. It's the rhythms of your night sky, and it will, in a way, connect you to our ancestors who were very familiar with all of this. One final tip, come out to a HAL star party to get answers to your questions. We are more than happy to have you come out and ask us, hey, what's that star? Or how do you do this or that? So hopefully we will see you as the star parties ramp up next year. And I'm just going to include in the slides here a couple of resources in case you want to, because the slide deck will be posted online after we're done with this. And that, folks, concludes my orientation. Hopefully it was helpful. Hopefully I didn't run too far over. Any particular questions?
Thanks. That was fantastic, Jim. Yeah,
That was
yeah,
wonderful.
Thank you.
yeah. We're going to switch gears. We're going to take a hard left turn into telescope gear. So if you want, if you have questions, that might be a good time to hit Jim with them now. Okay. So maybe if you think of something afterwards, you can ask at the end of the meeting. Okay, I'm going to share my screen again. Thank you, Jim. That was really cool.
You're welcome.
Yeah, can everybody see my screen now?
Yep.
Okay. So I'm going to give a quick kind of a fire hose treatment about telescopes and telescope gear. And don't feel like you need to learn all of this all at once, but and also please ask questions if anything isn't clear. So here's the outline for this presentation. We'll talk about telescope types, key properties of what you care about with a telescope, and then the other part, which is basically the other half of what you're using to see something, is the eyepieces. And we'll talk about telescope mounts and telescope accessories. So there's three main categories of telescopes. As pointed out, there's refractors, reflectors, and kind of a hybrid, a mix of refractors and reflectors called catadioptrics. I said that right. So the first type is kind of like the most obvious kind, which is the refractor. And this is, Jim mentioned the Galilean moons. This is what, 500 years ago, some glass maker went, he picked up a piece of glass that had a curvature to it and another one, and he put them near each other, and he said, oh, if I put these in a certain way, I get magnification. And then a little bit after that, it was formalized, and then Galileo 410 years ago or whatever, used it to see the Jupiter's moons, hence the name Galilean moons. So that scope on the left, on the bottom left down here, that is very similar. It might even be a Galileo scope. I forget where I grabbed the picture online. These charts will also be posted, and there's little links to where online on each slide if you want to pursue further. Sometimes you see these refractors with a little right diagonal at the back so that it's easier to look down, and depending on where you're looking. If you're looking really high in the sky, it's hard to get underneath the telescope, so you'll see this little right angle bender. It's basically a mirror. But for all intents and purposes, a refractor has a single or complex set of objective lenses. That's the main lens that captures the light and focuses it down. The length of that distance from the focal point to the lens is called the focal length. And then your eyepiece is like a mini telescope on the other side. It takes the light rays that just got collimated to a point, and as they stretch out, it kind of undoes what the objective lens does, is it takes those light rays and turns them back from a diverging cone into a little parallel plane wave that your eye can pick up and see. So it's kind of straightforward what's going on. And there's all refractors. There's all sorts of different classes of refractors. The most common ones that people use, if you look at this simple lens here, different colors of light because of the properties of refraction. Different colors of light will focus to a different point. So people have, over the history of telescope making in the last 400 years, people have figured out how to combine different lenses with different refractive indices and different shapes to make all those colors focus at the same point. Those are called achromats when that happens. And then if you do that, it's the number of just how complicated the number of lenses. If you do it with 3 colors, you get an achromat. If you do it with 4 colors, you get an apochromat, which is even less subject to this chromatic aberration. They call that issue when the light spreads out. So advantages of refractors is that they're generally really high quality. They don't require a lot of maintenance. You just take them, you set them up. The disadvantages is that they tend to be heavy because they have a lot of glass in them. If you want one that has any kind of magnification, it tends to be kind of big physically. And because all this glass is, very carefully bending and focusing the light, that it's got to be made very carefully. We have our telescope maker here who can attest that, they tend to be costly. Okay, so the second type are Newtonians. We got all these famous old scientific Galileo, and now we'll bring up Newton. So at some point, during the development of the telescope, Newton realized, hey, glass is hard to, quality glass is hard to get made without imperfections and impurities, given the technology of the day. And you notice like, hey, it's actually easier to make a flat mirror or even a curved mirror. The amount of the technology of the day was able to produce larger quality mirrors than they were able to produce larger quality glass. So he came up with a different type of telescope that did not involve any glass at all, except for your eyepiece. And so what happens with the Newtonian is the light comes in down the tube, it hits this primary mirror on the back, which then focuses the light to a point near the front of the telescope where you have what they call the pickoff mirror, a secondary mirror, which takes those light rays and shoots them off to the side, where then you can take the eyepiece and look at the image. The advantage of these is that you can get a much bigger mirror than you can a big glass complex lens. That you can make a large mirror is simpler, will weigh less, is less expensive to make. And because you're not passing through the glass, you don't have that chromatic aberration. You have other aberrations, coma and other things that need to be corrected, which is another class. But anyways, if you're looking for aperture at a lower cost, a Newtonian is the way to go. They're easy to maintain, although you do have to collimate them every now and again. Oh, okay, I said that here. Yeah, and because they're open, they're susceptible to dust. And there's some reasons why there are optical aberrations. And because they're big, sometimes they're not as portable. But if you're looking for aperture at low cost, that's the ticket. And then the third type of telescope, which is kind of like the best of both worlds, is a catadioptric. Schmidt-Cassegrain. There are other kinds like Maxutovs and oh, we got a telescope in the room. So we've got Maxutov Cassegrains and Ritchie Chrétiens, where these are the evolution of this some glass and some mirror. You use it's kind of like the Newtonian, where you have a big mirror and primary in the back, but you use glass in the front to do a little bit of a correction. And in this case, instead of coming out the side, you have the light rays folded back down through an aperture in the primary mirror. And so a lot of times you'll see a telescope like this. There's one that somebody just brought one in the room. This telescope is relatively short compared to its focal length because the light rays are bent, it's like they're folded over each other. So this thing might have the thing might be 20 inches long and have a focal length that is 2 meters or something. So the advantages of these are that they're much more portable, they're versatile, they're useful. It's like time proves things, like what people tend to gravitate towards and use over time. And like these are pretty good for planets, they're pretty good for deep sky, they're pretty good for, they do a lot of things well. They do nothing perfect. If you really want to look at, pinpoint stars, then a high quality refractor is the way to go. If you're looking for a super dim fuzzy object, you can get a big Newtonian mirror. But these guys are a good compromise. One of the disadvantages is that these things, because they're closed up, it sometimes takes them a little while to cool down. And the cost is kind of halfway in between the two. So those are the three main kinds of telescopes. So what is it that it makes these, what are the properties of each and any of these telescopes that is important? And the first one, people, and I've heard this phrase many times, like aperture is king, like the aperture of your telescope, which is the diameter of the light bucket that's capturing the light, this cylindrical structure. The diameter is, so the diameter of that lens or primary mirror, it basically tells you how much light you're going to gather and focus down. Ultimately, your eye has an aperture of a few millimeters. If you're young, it might be 6 millimeters. If as you get older, it gets a little smaller. The maximum diameter of the opening in your eye, the pupil. And so what you're doing is you're using the telescope to gather as much light as the size of the telescope and focus those rays and concentrate them down into something that is roughly the diameter of your pupil of your eye. It's like making your eye bigger, if you will. And so how dim an object you can see is determined by the area of the aperture. And there's and also there's a bunch of physics of diffraction and other properties of the size of the structure, which tells you, when it's a bunch of Fourier transforms and stuff that we don't want to talk about. I don't want to talk about. But your resolving power is related to that aperture as well. So the larger your aperture, the finer details it's able to pick out in what's known as the airy ring or the airy disk. So this graph here kind of shows for different aperture sizes how the resolution gets smaller and the limiting magnitude. Jim talked about the magnitude of a star. 6 is the lowest magnitude star that you can see with your naked eye. But if you have a 4-inch refracting telescope, my eyes are doing good. Oh, wrong glasses. If you have a 4-inch refracting or 4-inch telescope, you can see something like magnitude 12. If with a 8-inch you can see magnitude 13 or something like that, if you're in dark enough skies. So the aperture really is the most fundamental parameter that describes your telescope. The other thing is the focal length, how long the path to this focal length. And when you look at the focal length of your primary objective lens and the focal length of your eyepiece, that basically determines the magnification. The factor of how many times closer something looks. Then the other mysterious thing that people talk about is the F number. If you're a camera buff, you know about F number. The F number is how fast your lens is. Basically, if you divide the focal length by the aperture, that is something called the F number. And so why is that important? It's because if you think about a shorter focal length, you'll be concentrating those fields, you'll be concentrating all the light rays much more quickly on a shorter focal length. So a lower F number concentrates the light rays more, which means if you're using it for on a regular camera, your lens is faster, meaning for a given for a given ISO, you can have a shorter exposure time and capture the same brightness. So lower F numbers mean a more concentrated, and so if you're into astrophotography, you want a relatively low F number scope if you're going to try to capture dim objects. So there's others, but those are the main three, at least as I see it. And by the way, I'm not a professional. I'm an amateur. So if anybody has questions that I can't answer, I think we have some other people in the room who might know how to answer these better than I can. Anyways, and then so people focus on telescopes, but those last charts, the light rays, the same amount of light energy that goes through other than a little bit less for attenuation or whatever, but the same light rays that go through your big objective lens. So you buy the most expensive, beautiful telescope in the world, and then you put a crappy eyepiece behind it, and you're going to distort all of the light rays, all the light rays that you paid so much for and worked so hard to gather and collimate and collect and focus, because the second half of the equation is it's undoing what the main objective lens did in some sense. So it's almost really as important to pick a quality eyepiece if you're gonna, enjoy the view. And so just like the telescope, now these lenses, just like telescopes, they have there's different classes of eyepieces that range in price and range in some of the critical parameters. Generally more glass pieces of glass you'll suffer a little bit of attenuation, but they often provide better views, wider views, and another parameter that's important called eye relief, which is how far your eye can be back from the lens and still capture the full field of view of the eyepiece. So some of these gigantic, expensive eyepieces, you'll find if you really get into the hobby that they're worth their price.
Question, Victor?
Anyways, the key properties are the focal length, the barrel size. You see some of these have a small barrel and some of them have a 2. The standards are 1 1/4 and 2 inches. There was an old one, 0.965, which you hardly ever see other than in 1975 department store telescopes. So, if you have some of these 0.965s, they won't be that useful, generally speaking.
Question,
then-
Victor?
Yes,
Can I ask a
please.
question? Hi, Joel here. If you're not as much into astrophotography and you're just getting started, are there reasons or advantages for a slower telescope?
Yes. So, can I answer that in the next slide?
Sure. Thank you.
If I remember what my slides are. No, I don't have it in the next slide. In the last slide, I mentioned magnification. If you're interested in looking at planets, so the slower scopes won't focus the light rays as intensely. So you might have like a really long, like those refractors I showed at the beginning, those long tubes. They may have a very high F number, 15 or higher, meaning the focal length is much longer than the diameter of the lens. And so for telescopes like that, the magnification, the magnification, I thought I had it on one of these slides. Oh, here it is. So the magnification is the focal length of your telescope divided by the focal length of your eyepiece. So the focal length of your eyepiece may be 20 millimeters, it may be 10 millimeters, it may be 30 millimeters. If your focal length, if you're trying to look at planets, you're generally not interested in gathering a lot of light because planets are relatively bright, they're not dim. So you don't need to concentrate the light rays as much, but what you do want, since the planets are so small, you do want a lot of magnification. So for a given eyepiece, a slow telescope will generally be better for viewing, small objects like planets, small bright objects. So yeah, if you're a photographer, you want a fast telescope. But if you're into visual and particularly into, sorry it took me so long to answer that question, but the answer is yeah, you might want a slow scope if you're into looking at planets.
Thank you. No, that's a good explanation. Thank you.
Okay. So as I mentioned, the design, there's all these different designs, dating from antiquity to recent times with Al Nagler, who spoke to the club last year or the year before. The design of these eyepieces, just like the design of the telescopes, will determine these critical properties like apparent field of view, like how wide the field will actually be. Apparent field of view is your actual field of view is the apparent field of view divided by the magnification. But the field of view and eye relief are the two main parameters that the focal length, field of AF, apparent field of view, and eye relief are the things to look for in eyepieces. And price, because they vary a lot. Okay, so that's telescopes. I guess I only have a few more slides. What about telescope mounts? So, there are two main kinds of mounts. There's Alt-Az, which, kind of is most intuitive one. You set it up on a tripod and you can move your telescope up and down. And, that's altitude, and you can move it left and right, that's azimuth. If you're looking at the meridian, you're talking east, west, and north, south with those degrees of freedom. These mounts are generally less expensive. The other kind of mount is an equatorial mount, which I'll talk about in a second. These Alt-Az's are generally much cheaper. They're easier to use. They're simpler, but they're not useful. If you're into astrophotography, they're not useful for long exposures because they don't track the night sky in the way that the night sky moves. So what happens is if you track something in Alt-Az, the field of view will wind up rotating as you track something over time. And just like they can be manual or computer controlled. And in modern times, our generation, the Dobsonian, I can't remember his first name. John, thank you. John Dobson came up with this very clever way to implement a way to put a big mirror on the bottom of a base with a rocker and a rotator, and then with some, you can have a Newtonian that's very lightweight with the rods and whatnot, and the pickoff mirror is up here. But the primary mirror is the heavy thing. With his very clever creation of this simple mechanism for moving it, really expanded the hobby because people could take very, very, very large apertures, portable, take them with them. So that's an Alt-Az mount. And the other kind of mount, if you're into astrophotography, you need one of these, is a equatorial mount. And this mount has two axes as well. But what you do, that Jim talked about Polaris, you have to align one of the axes with Polaris if you're in the northern hemisphere. In the southern hemisphere, you have to, there's another way to do it. There is no star on the axis in the southern hemisphere. You have to use the pointer stars of the Southern Cross, and there's another little trick that you use down there. I was lucky enough to live in the southern hemisphere and had to do that for a while. But anyways, you take this the polar axis and you point it directly at Polaris, and when you do that, now the two axes that you have are right ascension and declination. Right ascension is just one thing which moves in exactly the opposite way that the Earth rotates. The Earth is rotating this way. You take your right ascension axis and you move it in the exact opposite way, and your object that you're looking at will stay exactly perfectly in the field of view without any rotation or any strange effects. And then declination is how far, depending on what you're looking at, you need to adjust the declination. And so these are the other thing that's nice about equatorials is that they can be used with any kind of telescope. You can put a refractor, or you can put a Newtonian or whatever. The downsides of equatorials are they take a lot of time. They tend to be a little more complex, heavier, and may take more time to set up to get them polar aligned and whatnot. And I don't think I've seen one of these. Actually, I have, but generally these tend to be computer controlled. Okay, and then the last slide I have is accessories, and I'm going to just not even spend any time on this because if you're into this hobby, you can spend a lot of money buying things and to make your life easier, all sorts of things. And I'm taking up too much time, so I'm going to just move on and say, if you want to talk about it, if you're interested and really want to talk about this offline, then let's talk afterwards or at a member start party or something. But there's all sorts of things to help you out and make things better and easier, and et cetera, et cetera. Okay, so then I'll turn it over to, any questions? If you think of something afterwards, just come up and approach me, or we can talk offline. Jim, you want to? Thank you. Oh, you're in my driver, you want?
No, I'll hit the, space bar to advance when I'm ready, so.
Okay.
Got that. Thank you. Thank you, Victor. Talk about visual versus, visual observing versus astrophotography. I think, most people, if they try to divide our hobby up into two parts, the visual observers and astrophotographers, and I don't want to try to tell you that one is better than the other. Full disclosure, I'm an avid astrophotographer, but I know a lot of visual observers who are very dedicated to what they do. So I'll talk a little bit about that. So visual, as the word applies, you're looking at things with your own eye. Sometimes you're looking at the night sky, looking at meteor showers, you're looking for constellations. Some of the things Jim talked about, looking for planets. You don't necessarily have to have any magnification to find these things. So just, go out there and look for them and get familiar with the night sky, how it moves and all that. If you want to see the object in more detail, you're going to need a pair of binoculars or a telescope or something like that. So visual observers come across the whole gambit of observing techniques: naked eye, binoculars, different types of telescopes. Some people like looking at planets. Some people like looking at nebula. Some people like looking at star clusters. There's just all kinds of visual observers out there. We had a very talented visual observer who we lost a couple years ago, Bob Prokop. If you ever sat in the field with him and just having a conversation, you bring something up, oh, that's over here. He's got a telescope on an Altaz mount, and he just pushes it, and there it is, and he shows it to you. You have a wonderful night out there with him. There's a visual observer right there who can relate to what I'm talking about. Some visual observers, I'm going to save that for just a little bit later. We'll talk about combination of visual and astrophotography. But visual observers want to see it with their own eye. They want to see the thing, that they want to hunt it down. They want to see it with their own eye, and that's what they work on. They work on those skills. The equipment is, if you do use equipment, the equipment is pretty simple. Usually a tripod, some kind of a mount, and a telescope, and then an eyepiece and your eye. And it's really, well, you might need a dew strap, you might need a Telrad, things that Victor talked about that makes your life easier, but it's kind of fairly well contained. Some visual observers, after a while, they become bored with seeing. There's a lot of reasons why people are transitioning, but one of them is to get bored with seeing the same old fuzzy objects year in and year out. And light pollution makes that even harder. Trying to get to a dark sky site actually, let me add here. Victor talked about aperture being a big determinant of what you can see. A dark sky opens up more things for you to see than even aperture does. So keep that in mind. So people get kind of bored with that, and what the heck, I'll put a camera on the back of this telescope. Take the eyepiece out, put a camera back there, and now you're an astrophotographer, and your world just changed. Some people continue to do both over the course of their journey through the hobby, but some people just strictly do astrophotography. It gets a little more complicated. It's a lot more complicated. It gets as complicated as you want it to be. You're going to probably have a German equatorial mount, depending upon what you're photographing, whether it's planets with as Victor said, a slow telescope, one with a long focal length. Photographing planets, you're gonna want one type of telescope. If you're photographing large, deep space objects like the North American Nebula, Great Orion Nebula, Andromeda Galaxy, these large targets, you're gonna need a shorter focal length telescope. Probably gonna be working with a refracting telescope, a faster refracting telescope. When I was doing planetary, I was working with a 2400 millimeter focal length 12-inch telescope, and I put a 2.5 2.5x power mate on there. And I was working at about 6 or 7,000 millimeters of focal length to make Jupiter look like something that you can see in a photograph. When I'm doing deep space work, like Andromeda Galaxy, and I'll show you a picture here in a little bit, I'm working at 430 millimeters of focal length with a 4-inch scope. And it's like, two completely different things. Another aspect of astrophotography, you might see like C-Star is new. People are using those. Very easy to set up, very easy to operate, and you get an image with fairly little effort. Now I'm ready to talk about the person that I almost brought up earlier, Richard Ord is a very talented sketch artist. He's done hundreds of sketches of planets, nebulae, galaxies, you name it. He's done sketches out there, and I'll show you one of those in a minute. He also has a teleview intensifier, and I've looked at one just holding it up to the sky and scanned the Milky Way, and things that I couldn't even see with a telescope and an eyepiece like North America Nebula. I could see it without any magnification. It was like, boom, there it is, right there. But he will sketch while his C-Star is imaging. So he's kind of doing both at the same time, doing one on one session, one on the other. He's doing both in the same session. Visual observers will look at astrophotographers and say, why do you do this? You know, you can re-ask our own selves that, so it's okay. Why do you do this? The images are already there, probably better than what you can do, and it's going to cost you a lot less and a whole lot less aggravation. Well, the aggravation is probably part of it. To build an imaging system, the telescope, a camera, might go monochrome, or you might go one-shot color, so monochrome and a filter wheel in there. Focus is not constant all night. You want to focus a lot, especially when you're changing filters. And it's one thing leads to another, leads to another. Software is pretty involved to do all this. Processing is involved, but photographers like the challenge of putting together the system, operating it, having a physical artifact that they can share with others, and maybe even something to print and hang on the wall. So that's kind of what drives astrophotographers. I think I want to stop there and go into the next topic. Any questions on visual versus astrophotography?
When you said hanging on the wall, you reminded me that.
Oh, I do have one.
The slide on the room back there.
Yeah.
Our other former,
Other
former club president, took that picture, and it's been on the wall for years here now.
Okay, so this is Richard Ord's sketch.
Oh, you want them dimmer?
How this we do it?
Yeah, I have them all.
You could use that down too. So this is Richard Orr's sketch of M31, the Andromeda Galaxy. I believe somebody's going to be talking about NGC 206 tonight. So there it is in his sketch. And you can compare that to what you see in an astrophotograph. The difference between what you can see is basically your eye can only, as a photon hits, it only has an effect for like 1/50th of a second or some short period of time like that. So that's all the light that your eye can gather at one time. The astrophotograph is, this particular one is 10 and a half hours of exposure time. You can see NGC 206 in the bottom left of mine. You can see the M32 down here. You can actually see that the scale, Richard's scale is larger or smaller. I'm not sure. So mine is kind of compressed a little bit because you see M32 and M110 are closer together. But that's about what you see at the eyepiece for any beginners that have not even looked through a telescope yet can get a sense of what the difference between visual and astrophotography is. Now let's take questions. If there are any, yes.
Would you recommend using cell phone holders?
Using what?
Cell phone adapters?
That's a great question. That's another way of doing astrophotography. Basically, when you do that, you put an eyepiece on a telescope, you put a put the bracket that will hold it in place, hold your camera over the eyepiece, and you can take photographs. I've not done that. I've seen a little bit of work for that, and it's actually pretty interesting. And that's another aspect of another way to go about astrophotography. I would recommend or not recommend it. It's just, if you're interested, try it. The bracket might spend $80 or $90 for a bracket, and
I found it to be not useful.
not useful. Okay.
Despite what they claim, it's very difficult to focus the lenses of the lenses of your phone to that of the eyepiece. It's very difficult.
Okay.
Even if you go for $100 or $200 mount, and cell phone holder mount, it doesn't work.
Okay.
So that's why I asked you whether you heard about this. Either buy this and thinking they can photograph like this.
I would say maybe 6 or 8 years ago, I saw not a lot, but some people experimenting with it, and I don't see as much of that anymore. So maybe everybody found the same thing that you did. The reason why you need an equatorial mount to take astrophotographs, be exposed for 10 and a half hours. That was over 3 nights. And probably, I'd say about 200 different subframes were stacked to make that that image. So,
It's quite an achievement.
thank you.
So which telescope do you use to capture it?
My telescope for that is a 4-inch refractor. Teleview NP101 IS. Made by designed by Al Nagler, who Victor mentioned just a little while ago. Any other questions? All right, so I'll step into my next topic.
I don't have any slides for that.
Okay, no slides. So
Did I?
These are, no, I just,
Okay.
these are pretty pictures up there while I talk about the next topic. Next topic that Victor signed me up for was what did I call this? Leadership opportunities, service opportunities in HAL.
Yeah.
So as a beginner, I'd be interested in knowing about some of these things. And I'll kind of talk about my journey through HAL and kind of hit the things along the way that are service opportunities.
Jim, if I could, we're running a little behind, and I hate to say this because this is important for the club, but just, if you could.
Okay,
Not
go-
spend,
go
not spend a
fast.
full 15 minutes.
Joined HAL in 2012. And 2014, the effort started to bring together the observatory and put the Watson telescope in it. There was a call that went out, said, hey, come out and be part of this, and I did that. Started there, and that was kind of like a project oriented thing. So if you're interested in that, if something comes along, jump in and give a hand, and you'll be surprised at how quickly they'll draw you in. While I was doing that, I also became a park key holder, which meant that I was qualified to host star parties, the members only, the public star parties and the impromptus. So I did that for a while. If you're a key holder, you can call an impromptu. You basically have to be the one to lock up the park at the end of the night. But you'll be called on to probably host two star parties a year.
One members and one public.
Okay, so 2 star parties a year, so the workload's not hard, and you can come out here, you can call it an impromptu anytime you want on a clear night. The other thing I did is the observatory came online. I trained up on the Watson telescope, and I was a CT. That's in the initial tranche of CTOs. Very interesting to learn how to use that ancient thing, and I enjoyed it. While we were doing that, putting all that together, I was invited to run for election, to be on the HAL board of directors. This club doesn't run itself. The CTO, the key holders, CTOs, and the board of directors make this club go. And people like Crystal back there, who's our librarian. These are all service opportunities where you can help make it go. You don't have to be an expert astronomer. You don't have to actually I've recruited people onto the board who knew next to nothing about astronomy. And actually that's a good way to learn more about astronomy, because you're exposed to more stuff. So serving on the board, elections coming up in the January meeting, so think about running for a seat on the board. Even after the board, so I served on the board as secretary for 2 terms, president for 2 terms, and I've been up until this year, I've been involved in the board running the elections. So my board services span 10 years. I have people like Joel Goodman. I don't know how long he's been on the board. Chaz Grimpo retired from the board 2 years ago, and I don't know how long he was on the board. Phil Whitebloom was the president behind me. He and I thought that he had been on the board as president for 3 years, and we got to add up the numbers, and turned out it was 4. We don't know how that happened. So, but what I can guarantee you is you will never see how the same way again once you serve on the board. I would highly recommend that you do it. Don't have to be a genius. Don't have to be a crack astronomer. Just somebody that's willing to roll up their sleeves. The workload is manageable. The board culture is of such that people will explain to you what goes on. You pick it up real quick, and you're on your way. So consider that. Any questions for me? I think I'm done.
What is the CTO?
Certified telescope operator. So you work in the observatory, run the telescope. Sorry about that.
All right, thank you. I
Thank you.
appreciate that. Okay, next we have a special presentation from our sister organization. We have Chris Bennett, who's going to talk about NGC 206.
I saw a little picture of it there, maybe it was kind of hard to see, it was down in the, where it was split, so it was
Yeah,
left corner.
I flipped my picture to, Richard sketched his doing, a diagonal, so I flipped mine to match his.
So, when you go out and look at the night sky, almost everything that you can see, stars and star clusters and everything else, are very close. You don't realize how close they are. The Pleiades, what, about 450 light years away, something like that? Seems like a long ways, but it's not. So a lot of the clusters, maybe 1,000, couple thousand light years. Even the globular clusters are around tens of thousands, something like that, and 13s, 20 something thousand. That cluster right up there, about 2.5 million light years away. So this is a little bit of a challenge for the visual observers, not so much for the imagers. Still you can't go out with the DSLR with a lens on it and get a good picture of a star cluster in a galaxy 2.5 million light or 2.4 million light years away. Technically, it's not a cluster. It looks like a cluster. Common sense of the word, it's a cluster of stars, but it's big. It's huge. It's about 200,000 solar mass cluster of stars. And if you think about it, if you were in that galaxy and you were in the vicinity of that galaxy, you look up in the night sky, you wouldn't even notice it because it would cover the entire swath of the sky that you would see. So it would just be a very thick cloud of stars. So it's technically not a cluster. It's an association. They call it a stellar association. The biggest difference is they're big and they're not quite as densely packed as like a globular cluster would be. Some of them have around the same mass as a globular cluster, but they're not as dense. So these are a little bit more spread out. But from our vantage point, this one looks like a star cluster. We do have some in our own galaxy, like Orion OB1 is a pretty well-known one. It covers most of the constellation of Orion, and you can't really tell it's there because it's you have to look at the motion of the stars, the proper motion to find out actually they belong to a cluster of stars. But anyway, so this one is actually two parts. Got 2 parts on it.
Oh, did you?
Who's gonna control?
Did you want? Are you good?
Well,
You want to drive? You want me to?
yeah, go back one. So it's actually got anyway, there's 2 parts. Yeah, it's actually 2 clusters. One of them is about 10 billion years old, and the other one is about 40-ish million years old, which is pretty young for a star in any cluster. The reason that these are very hot, bright stars, high mass stars, and the reason these clusters are these clusters are young is because these stars don't live that long. Some of the stars, the blue supergiants in this cluster have a lifespan of about 10 million years, as compared to the sun's lifespan of got about 4 billion years left on it, so it's about an 8 to 10 billion year lifespan of our sun. These are somewhere around 10 billion years. Some of them are in the lower mass stars. Part of the cluster is older, about 40 million years old. And those are mostly Cepheid stars and things like that. But there's some of them in there that are 100 times the mass of the sun. So they burn very quickly and very bright, and almost 1 million times the luminosity of our sun, which is one of the reasons you can see this cluster 2.5 million light years away. This is from a 0.9 meter telescope out at Kitt Peak. It won't look like this when you look at it. But it was at about 35 inches or so. So hit the next one. This is basically what I said. It's about 40 arc minutes away from the core of the galaxy. About 4.2 arc minutes across, which is very small in field of view. About 4,000 light years across. You notice around the edges of that cluster, there were some those red areas. that was taken with a hydrogen alpha filter, which is ionized hydrogen. In those areas of star formation around the outside is where new stars are being born. There's not actually any star formation going on in the cluster anymore because all the molecular hydrogen got blown out by the radiation pressure from the very bright star. And that's one. So there's also a lot of Cepheids in there as well. So those are also very bright variable stars. Probably seen M31 if you've been around for a while. And if you're new to the game, it's actually a good one to start with. It's pretty easy to find. I usually start, can't see part of it. There's this great square Pegasus here. You can't miss it. It's big, bigger than you probably think it is when you go out and when you look in the southeast, high in the southeast now, you'll see a huge square of stars up there. Can't miss it. The bright one there on the corner is Alpha Andromeda or Alpherox, and that's usually white. I go from that one to that one. That's Delta, that's Beta, Mu, and U. So you just go little dog leg up to M31, and it's pretty easy to find. Even with binoculars, it's pretty easy to find. Some people go from Alpha Cas all the way down that way, but there's a lot of real estate in there. They'll probably get lost. Easiest one is from Pegasus. All right, next. All right, this little finder chart of it, close up. This is the north, up, east, left, which is the standard way they do the charts. The circle in the center there is about 50 arc minutes field of view. That's my telescope, the 2500 millimeter or the 21 millimeter ethos. So that's a pretty standard long telescope field of view, 50 arc minutes across there. And this is a little close up of the part in the square. And you can definitely see with a decent sized telescope. You will not see it with a very small. You will not see it visually with a very small refractor telescope. Or probably you can in that dark sky, but not East Coast Maryland. You won't see it with a small telescope visually. But with maybe an 8-inch Schmidt or something like that, it's pretty easy to pick out that small little glowing cluster here. You won't see a lot of detail, and it'll just be a bright little smudge in there. What you will definitely see are the dust lanes. So you can definitely see the dust lanes going through here, and there's some that go up around each side of it. And so that's what you want to look for if you're looking for it visually. There's a couple of markers you saw on there. M32 was off to the east there. There was a 7th magnitude star also. That might help you out with the orientation as well if you're looking for it visually, because it's not really bright and it's not obvious. So you find the M32, which is very bright, brighter, has a brighter surface brightness than M31 does, just smaller, brighter. And HD 3914, about 7th magnitude. Those two will make a little triangle there and make it pretty easy to find it. Next, yeah. There's a little bit of a close-up. There's 10 arc minutes by 10 arc minutes. So depending on your telescope, this is about I don't remember what the field magnification is, about 250 or so with my big scope. So what you'll see in there is the cluster about 4 arc seconds or 4 arc minutes across, and that's just this section up in here. And the modeled stars in there are actually in the cluster. They're very bright, super blue supergiants and luminous blue variables and things like that. Some of the brighter stars in there are actually field stars. So you know, these are field stars. That one's not a field star. That's down there.
Supernova?
Globular cluster.
Oh, which one?
This one right here. Yeah, so those 4 in a little cup, and then the one above it is a globular cluster. There's about 700 or 800 of them in Andromeda if you want to go hunting for globular clusters. It's you thought summer was globular cluster season. You can do it in the winter too. They're a little harder to find, but yes, you can definitely, you won't see them visually, probably only 2 or 3 of them that you can see visually. But with a imaging setup, you can definitely find a couple of hundred globular clusters in 31.
About how many stars are in the NGC 206?
There is it's a mass of about 200,000 solar mass. But a lot of those stars are very low mass and you can't see them. And a lot of them are very high mass. So the number of actual individual stars, it's hard to say. There's a lot. It's probably about 200,000 because most of them would be lower mass and then quite a few of them would be higher. They determine the mass of it by its motion and by its luminosity, like aggregated luminosity. So it's hard to count them. You can't really count them individually, but you can see the bright one. You can give it a good guess. So 200,000 or so. All right. This is from last weekend. This is just an air mass chart. It's up early in the evening, so you don't have to wait around until late at night or anything. This chart was from last weekend. Just shift that to the right a little bit. And the moon was up last weekend too, but it's not now. It's cloudy now though. So, but anyway, for quite a while, it'll be up early in the evening, and it'll be up for most of the night, at least until early morning. So it's a good time of the year to go out for M31 and MGC 206, or maybe some globular clusters if you're really adventurous.
Cool.
And that's it.
Yeah, thank you so much. You've given me something to do with my 11-inch SCP.
I didn't mention it. There's a little atlas that was published in the 80s called Atlas of the Andromeda Galaxy by Paul Hodges. Paul Hodge has lists and charts and a lot of the things in there. It's a little out of date, but it's online. You can look it up. You can use that to find a lot of interesting things. And there's about 180 or so associations and several hundred globular clusters. If you want to find something to keep it busy for the rest of the winter.
Terrific. Thanks. Yes, Ian.
Yeah, some of those clusters are in the Globular Cluster Astronomical League award.
Yeah.
Oh, okay. So one of the programs
Club.
has
I haven't
those
done that.
clusters in.
There's a few of them that you can see visually.
Okay.
The vast majority you can.
Okay, so I'm on the slide like 23 of 58, and we need to vacate in 10 minutes. So I think what we'll do is we'll save all the members as Astro Images and sketches for next month. And Wayne, if it's okay with you, can we defer that until the next meeting, your What's Up in Space? And maybe Jim, can you go through your shallow sky stuff really quickly? Would that work, you think?
Sure, let's go ahead.
Okay.
Okay, so a little planet rundown. Venus is well away from the sun. It's low in Sagittarius. Sagittarius isn't very, obviously it's like the basement of the zodiac for us. So catch it early in the evening. Its phase is going to decrease from 71% to 60%, but its size is going to increase from 16 arc seconds to 20 arc seconds. The moon on December the 14th will make a very nice pairing with it. It'll be a great photographic opportunity. Mars is still a late evening, early morning target in Cancer, but it is up to 10 arc seconds, which is considered the threshold for visual observing. It'll get another 3 arc seconds in size over the next 4 weeks on its way to its January opposition. So basically, the next 12 weeks are your best chance to catch things like the North Polar Hood and the dark features such as Syrtis Major visually in the eyepiece. Next. Jupiter's going to hit opposition December 7th in a couple of weeks. It'll be in the sky all night long. King of the Planets always has a wealth of cloud details for those that are willing to take a little time and observe it. Don't rush it. Spend like 10 minutes looking at it and your eye will gradually pick out features. Next. And Saturn is still pretty well placed for observing, but it starts out just on or past the meridian as twilight ends. So you basically want to jump on that early in the evening rather than waiting till later. Next. Okay, we get the Geminids this coming December 13th, 14th. It peaks in the afternoon for us, but still it's worth looking that night. Click again. The problem is that we do have a waxing moon. It's only going to be 2 days away from full. So you're only going to catch the brighter meteors, but click again. The good news is that there are usually a lot of bright meteors with the Geminids. It's one of the more productive showers, so definitely give it a try. Next. So we have a special event occurring Wednesday, this coming Wednesday. An occultation is basically defined as when one object is hidden from another, is hidden from view by another object that passes between them. So go ahead and click. The moon, as it goes around the zodiac, as it orbits the Earth, it covers stars and sometimes Messier objects. Click. There are basically only 4 bright first magnitude stars that can be occulted. One of those is Spica, and it will be covered by the moon this coming Wednesday, the 27th. Click. Disappearance at 5:35 a.m., 20 degrees high. There's a simulation of it there. Click again. Reappearance at 6:52 a.m. in twilight. As a side note, the weather forecast looks absolutely abysmal, so I don't think we're going to get to see it. But if it should happen to clear up, it was kind of that'll be a neat thing to see. And that's what's out in the shallow sky for next month.
Thank you, Jim. That was awesome. I was excited about this, and that I'm a late night, not a morning guy, so you lost me at 5:35 a.m. Anyways, all right, so we have a bunch of other stuff, but I think, Wayne, is that okay with you if we hold off on this until another?
Sure.
another
Yeah,
meeting?
you're out of time. It's all right.
Yeah, so I would just like to say to everybody who came here in person, especially those who submitted images, this was a great month for images. There's so many comets and so many planets and Jupiters and all sorts of nice deep sky stuff. Thank you guys so much for submitting. And I think what we'll do is during the December potluck, we'll just run a slideshow of your images, and we can talk to them in just casual way. And also
Posted, right?
and yes, it's in the slide, so it will be posted online. And also thank you to Ian Slepian, who gave me a nice set of charts describing how to do a C-star mosaic, but we'll maybe another meeting as well. So again, thank you guys so much for coming, and everybody online. It was a good contingent online. I'm sorry I didn't monitor the chat. I hope you guys, everybody online enjoyed the meeting and got something out of it. So other than that, thank you, and we'll see you at hopefully see you at the potluck and at events, and keep an eye out for impromptus, and also please take to heart Jim's comments about serving on the board if anybody's interested. I plan on running again for president next year, but if somebody was super excited and wanted to run against me, I would be very happy to, transition or whatever. But I'm sure many of the other board members also would love to have help or come on board. So thanks, and thanks for being part of HAL.
Thank you.
Thank you. Thank you.
Bye.
So I hope fun 2 weeks ago. I didn't think it was airborne.